In this video, we're going to look at an experiment that a student has designed. A student designs an experiment where she creates 3 calorimeters. Each calorimeter is made with a glass jar with a lid and holds a thermometer. The jar is surrounded by polystyrene, cardboard, or paper towel. Her design is to measure the temperature of 250 milliliters of water in each jar at the start of the experiment, then add 25.1 grams of ice to each calorimeter. Seal them in the jar, and measure each temperature at 4-minute intervals. Her data is included in the table below. So we've got the time and then the temperature for polystyrene, cardboard, paper, towel, calorimeters. And it says, what are the manipulated and responding variables in the student's experiment? So the student's manipulation is the kind of material that the calorimeter is made out of. And she's testing to see she's testing to see what the temperature change is. So the change in temperature is the response that she's recording and measuring. It says then, given the description of the experiment, what variables are controlled by the student? Well, she has the same mass of ice in each calorimeter, so that's controlled. She's got a glass jar that is being used in each calorimeter. That sounds like it's the same. And yes, those are kind of getting towards our controls. Which other variables should reasonably be controlled, and how would you suggest controlling them? Well, reasonably, she should be clarifying that the jar is the same for each of the experiments. She should be perhaps measuring a mass or surface area or something that these are these are comparable not just as substances, but amounts of those substances that are creating the insulation in some way. I don't know, maybe thickness of the polystyrene compared to cardboard compared to paper towel. It doesn't suggest that she did that. She's using a thermometer. Is it the same thermometer each time, or is it different? Or they did 3 different jars? It's not super clear. We know that the surrounding is, but those things should reasonably be controlled. One thing that probably is not reasonable to try to control is the environmental temperature. So sometimes people say that room temperature is controlled, but it is not. I mean, unless you're actually constructing a way to control that temperature, it's not really controlled. Or we're not intentionally trying to change it, but it might be, we don't know. And the best you'd be able to do with that is maybe monitor the temperature of the air around in the room as well, for comparison's sake. So, which calorimeter is most efficient? Well, an efficient calorimeter should have the least amount of heat loss. And so if I look at this, they're all starting at the same temperature. It looks like these get to be about the same temperature. But then if you look down to later trials, you'll see that polystyrene retains that lower temperature. It hasn't had as much heat transferred into the calorimeter as cardboard or paper towel. So this must be the most efficient. That's how I'm going to be able to tell. Which substance would you use to make an insulated drink container out of, based on the evidence? Well, I guess polystyrene is the best insulator. So I'd make an insulated drink container out of the best insulator. And then it says, what other considerations other than just efficiency should the manufacturer of insulated drink containers take into consideration? I think this is a bit redundant. But the other considerations might be, well, polystyrene is kind of a plastic. It's a polymer, and that's not good for the environment. So if we're creating disposable drink cups, I don't think polystyrene would be a good environmental choice. Cost might be a consideration. Let's think if the polystyrene could be recycled, though. Could we use polystyrene and that was used for something else and then be able to convert it into a polystyrene cup? Then we get a reusing quality. That'd be an environmental consideration as well. So there are a lot of things that could go into a decision like that as a manufacturer, other than just what is the temperature change going to be like, how good an insulator is. Although that is key to the job. Here it says the molar heat of fusion is the energy transferred by 1 mole of water as it changes from solid to liquid or liquid to solid. Calculate the molar enthalpy of fusion for the most efficient calorimeter, knowing that the mass of ice melted was 25.1 grams. Now, I've got two answers for this, and so I'm going to give you the simpler answer now, and then later I'm going to come back to this. It may be a separate video, but I'll do the simple version of this first. So the mass of the ice was 25.1 gram. Ice is just water. So the molar mass of water is 18.02 gram per mole. That lets me calculate the number of moles. It's mass over molar mass. And if I put that into my calculator, I can calculate what that is. So if I have 25.1 gram divided by 18.02 gram per mole, this is 1.39 mole of ice melts. Now, N delta H fusion, because we're talking about the ice now, melting or freezing, equals MC delta T. Well, my calorimeter has 200 grams of water, because it was 250 milliliters of water, specific heat capacity of water, and temperature change of water. My temperature change is the greatest change. It said my most efficient, so I want the difference between 13.9 and 19.4. And so my change in temperature is going to be 5.5 degrees Celsius, right? The delta T equals the 19.4 degrees Celsius minus 13.9 degrees Celsius, so it equals 5.5 degrees Celsius. Well, to get the heat of fusion, we'll take MC delta T and divide by molar enthalpy of fusion. We'll divide by N, so I get 250 gram times 4.19 joule per gram degrees Celsius times 5.5 degrees Celsius. The N is 1.39 mole, and so my molar enthalpy of fusion is that is going to be 250 times 4.19 times 5.5 divided by 1.39, and we get 4,144, so 4.1, or 4.1 I guess, because I have two sig digs, 4.1 kilojoule per mole. Now, the question then says, so that was the question. The book value for the molar heat of fusion of ice is 6.01 kilojoule per mole. So I actually look at that and I think that's pretty similar, considering we've lost quite a bit of heat just heating up the glass as well, right? Like the jar that's used is also using up some of the energy, so is the thermometer. So this seems like it's not too bad of value. It says for us to sketch a quick, so question 4 says sketch a quick graph of time versus temperature for the cardboard calorimeter. Is the process happening in ice endothermic or exothermic? So if the temperature starts out at 19.4 and then it heats up down to 14.1 and then it slowly starts to warm back up, and the delta T is the difference between the 19.4 and 14.1 for the cardboard calorimeter. So our delta T is the difference between those two values. Is the process happening to ice endothermic or exothermic? Well, ice is melting. So the ice is going to be taking energy from the environment, right? So the environment cools, So the change is endothermic, right? It's an endothermic change. The heat is being taken from the water and used to change the ice. More bonds are now being broken between the ice molecules, making them into liquid water. So solid to liquid. And it says, the last question says, use the molar enthalpy of formation from your data booklet to determine the